A satellite worth hundreds of millions can fail because of one empty fuel tank, one jammed mechanism, or one outdated component. Until now, there was usually no mechanic coming. On the 21st of July, 2026, a spacecraft called the Mission Robotic Vehicle launched carrying two dexterous robotic arms. Its destination is Geosynchronous orbit, roughly 36,000 kilometers above Earth. The public story is simple: a robot is going to service satellites. The buried signal is bigger. Space hardware may be moving from a disposable product into maintainable infrastructure. That change could alter how satellites are designed, financed, insured and defended. It could also create new risks, because the same machine able to repair a satellite can physically approach and manipulate one. The vehicle carries DARPA's robotic servicing of geosynchronous satellites payload, integrated onto a commercial spacecraft operated by Space Logistics, a Northrop Grumman company. NASA supported the program with simulation tools, software analysis and operators experienced in complex robotic procedures. The Naval Research Laboratory developed the twin robotic arms and servicing hardware. Each arm has 7 joints and can use interchangeable tools. The system is meant to inspect spacecraft, resolve anomalies, relocate satellites and install compact propulsion modules called mission extension pods. Those pods are effectively orbital jet packs. DARPA says they could extend a satellite's operating life by 6 years or more, especially when the satellite still works but lacks maneuvering fuel. That matters because geosynchronous satellites remain over the same region of Earth, making them valuable for communications, weather monitoring and national security. Their orbital positions are scarce and expensive. The traditional answer to failure was redundancy. Engineers added backup systems, extra fuel and conservative margins because no repair crew could arrive later. That made satellites heavier and more expensive before launch. A credible servicing market could change that calculation. Designers might launch lighter spacecraft, plan upgrades, or separate the long-lived platform from components that become obsolete quickly. But that future has not arrived yet. The Mission Robotic Vehicle is beginning a year-long journey using efficient electric propulsion to raise itself toward geosynchronous orbit. After arrival, it must complete checkout and demonstrate that it can approach valuable operating satellites safely. Close proximity operations leave almost no room for software, navigation or mechanical mistakes. Most satellites already in orbit were not built with standard servicing ports. The robot therefore needs cameras, lighting, specialized tools, and controls able to adapt to hardware never designed for repair. That is why this mission is more than a clever arm. It is an experiment in rendezvous, perception, force control, and decision-making around machines that cannot be brought into a workshop. The commercial structure is equally important. DARPA developed the robotic payload, while the company owns and operates the integrated vehicle and can later sell servicing missions. That arrangement is designed to move the technology beyond a one-off demonstration. After initial tests, the vehicle is expected to operate for more than a decade and potentially perform many servicing jobs. For satellite owners, the economics could be powerful. Extending the life of a functioning spacecraft may delay the cost and launch risk of replacing it with an entirely new one. Yet life extension can also slow renewal. Keeping old hardware alive may preserve outdated electronics, inefficient payloads, or vulnerable software longer than expected. Servicing also introduces dependency. A satellite designed around future maintenance assumes that compatible vehicles, tools, contracts, and permissions will still exist years later. Insurance markets will need evidence, not promises. A successful repair could protect an enormous asset, but an unsuccessful approach could damage both the customer satellite and the servicing vehicle. Standards are another hidden bottleneck. Industry groups have worked on rules for rendezvous and servicing because shared expectations are essential when one company's spacecraft approaches another company's property. Without clear interfaces and behavior, even a cooperative mission becomes difficult. Operators must agree on navigation data, approach corridors, authority, liability, and what happens if communication is lost. There is also an unavoidable security dimension. A machine that can inspect, move, or attach hardware to a satellite has capabilities that look different depending on who controls it and why it is approaching. That does not make servicing inherently hostile. Aircraft maintenance vehicles and tugboats also possess physical access. The issue is verification, consent, and predictable conduct in an environment with limited visibility. The mission therefore tests a social system as much as a robotic one: contracts, operating norms, data sharing, and trust between governments, manufacturers, insurers, and satellite owners. Another constraint is time. The vehicle launched in July 2026, but its electric propulsion climb means operational servicing is not immediate. The crucial demonstrations come after the long journey and checkout. So headlines describing routine space repair are premature. The launch proves the hardware has left Earth, not that every repair technique or business case has already succeeded. Still, the direction is clear. Other missions are testing orbital boosts and life extension in lower orbit, suggesting servicing is becoming a broader category rather than one isolated project. If these missions work, future satellites could be assembled with replaceable modules, refueled, repositioned or upgraded after launch. That would change the meaning of a spacecraft's end of life. It could reduce debris by preventing useful satellites from becoming abandoned objects too early. But servicing vehicles add traffic and maneuvers, so sustainability depends on careful operations, not robotics alone. The deepest shift may be financial. A satellite could become less like a sealed appliance and more like infrastructure with maintenance schedules, residual value, and upgrade pathways. That possibility changes investment decisions before launch. A company may accept different component lifetimes if it expects later service, while manufacturers may compete on compatibility and upgradability. But a serviceable future will require proof across many missions. One successful demonstration cannot establish pricing, reliability, international norms or universal interfaces for an entire orbital economy. The Mission Robotic Vehicle is therefore not merely a mechanic. It is a test of whether space can support maintenance, markets and rules around machines once considered unreachable. If it succeeds, the most important result may not be the first satellite it touches. It may be the moment spacecraft stop being disposable objects and become infrastructure designed to be looked after.